Swayam Prabha. Digital India. Educated India.
So, the overall theme of today's lecture will be catalyst. Okay, that is the basics I am going to teach, and this will be particularly focusing on chiral nano catalyst. So, title for this lecture is transition metal chiral nano catalyst for organic synthesis. So, you know what is catalyst, all right? You start studying about catalyst from 9th, 10th standards onwards. And in my last class, you learned about chiral catalyst. Yes, you remember a little bit? Asymmetric synthesis. I was talking about asymmetric synthesis. In asymmetric synthesis, you make optically active compounds, chiral compounds in optically active form, and to make it, you need chiral catalyst. Am I right? So, that much you are aware, at least from my talk. I don't know about others, they also might have touched that topic in different aspect. And today's lecture, I will be talking about nano catalyst. A transition metal, when you use normally catalyst, so they are homogeneous, you will say clear, you might have seen in organics lab, reaction mixtures you stir in the RB flask or reaction tube is a clear solution, colored but clear solution. Generally we call it homogeneous catalysis. Even you take a palladium 2 or 3, then take appropriate solvent, you will have a clear solution. Okay. Or you will see heterogeneous catalyst. You might have heard, am I right? Catalytic hydrogenation, which you are studying in your BSc. There are so many heterogeneous catalysts. So, this is a new concept emerged in the last 20 years, 20 to 25 years. Okay. So, using transition metal as a catalyst and sized in a very small nanometer size. Okay. And since my research group is involved in developing catalyst, particularly chiral catalyst, and this is the new project 15 years back we started using chiral nano catalyst. So, all the concept are putting together catalyst first of all, then chiral catalyst and that also nano sized. So, that is the theme what I am going to explain. So, in this lecture today we will be first talking about my research interest. What if you take a research group anywhere in the world, so they will have a theme, you cannot work in everything, am I right? There will be a theme. So, what is the theme for my research group, and in that one particular project will be, we are also working in developing new catalyst. That is a main theme for my research group. So, we will first I will talk about the research interest of my group, so that you will get, already you are working in lab for few days, some kind of idea you might have got it, am I right? So, then I will be talking about the basics. What is catalyst? Okay. What is chiral catalyst? That already you know. What is nano catalyst? Then finally, what is chiral nano catalyst? This is all basics. Okay. So, once you know the basics, then you can understand how to design a new catalyst. So, first you want to know, we want to make any new thing, that means we should know everything, am I right? So, what is the limitation in existing issues? Then, oh, this is the problem, by using this particular method or product, we are not able to do the particular thing. So, to overcome, we want to have a new model. That is the way, that should be the objective, am I right? Then based on your requirement, the objective you have to design, and that design should be better than existing models, am I right? Otherwise nobody will use your so you have a bike or scooter, 50,000 rupees, very nice, goes 80 kilometers, and somebody comes, makes a bike for 80,000 rupees, will go for only 60 kilometer. Which one you will buy? Obviously, am I right? So, what you make should be better than the previous one, am I right? Even after that also some people may not come, they will say I am used to this bike, why should I go to new bike? They are saying lightweight, it may fly, I mean that hesitation you will have, am I right? So, if you take most of our people, they think that always, it's recorded, so I should not talk other things, okay. So, any new design you make. So first of all, you should know the background. You should know the limitation. Then your design should overcome the limitation, and yours should be the best. Otherwise, nobody will use it. Okay. So that's what the basics first we will decide. Then we'll talk about how we are designing the catalyst and what is the reason for every component in the catalyst. Okay. Then we will be talking about synthesis of the catalyst very briefly and application. That's a real research part. Depends on the time. Very briefly I will touch. I will not go too much deep inside because that will be too much. Then I will be talking about the chiral nanocatalyst application. Only one slide. So it's ultimate aim. That's a aim, but it's not very successful. Okay, little bit successful is obtained. That I will discuss with you. Then finally I will wind up as I told you in the last talk. So I will be talking some of the options what you have after your MSc. So 10 to 15 minutes. That will be. You might have already heard from several faculty members from wherever you are coming. Your teachers or lecturers in your university might have discussed, but I will present my view. Okay, some good information you may have in this as well. Okay, so this is the plan for today's lecture. So if you take my research group at IIT Madras, as I told you in the last lecture, I am an organic chemist and particularly working in asymmetric synthesis. That's the overall aim. So, but that is also wide. Okay, that is very wide. So in that particularly, this is the overall organic synthesis, particularly that's asymmetric synthesis and catalysis. We develop new catalyst. For example, last time chiral catalyst, this time chiral nanocatalyst. The chiral portion is not very easy, I told you last time. So what I am going to present is nanocatalyst only. Attempt is chiral nanocatalyst. Okay, but when you desire, you should desire for a big. So for example, you are aiming for UPSC, IAS, IPS. For some reason, if you are not clearing it, you will be ending up with TNPSC first group. Yes or no? Am I right? You are aiming for TNPSC first. You may be ending with, if you are successful, is good. You may end up with TNPSC second group. Like that only. You aim first big. Dream. Have a dream. Am I right? Try to make it. If not, at least you will get slightly less than that. So that's the way the aim always, whether you are business or you are studying now or you are doing research, the aim should be novel, big, novel, to some extent possible. It should be realistic. If it is not realistic, then you will not achieve it. Am I right? So that's the point, you should have it. So in my research group, as I told you, we work in the area of organic synthesis and catalysis. Particularly organic synthesis, we develop new synthetic methodology. That means we try to develop new reactions. That's the main aim. And if you talk about catalyst, we work in three important areas of catalysis. The first one, you know that chiral catalyst. I discussed the basics of chiral catalyst in the last presentation, and also we work in the area of metal nanocatalyst. So I am not putting here chiral because it's not, though the design aim is chiral catalyst, it's not very successful the way it is successful, but not the way we thought. We are working on that. And third one, halogen bonding catalyst. So you may be, I don't know how many of you heard about halogen bonding. Nobody heard. Okay, hydrogen bonding. What is hydrogen bonding? Then where is hydrogen comes? Electronegative, two electronegative. No, it's not correct. Yeah. So hydrogen is here like electrophile, am I right? So you have hydrogen, then you have a nitrogen, am I right? Or sometime oxygen, and depends. So sometimes even some of the halogens. So that is non-covalent interaction. So bonds can be divided into covalent, non-covalent. Your carbon-carbon single bond, double bond, triple bond, am I right? Even metal ligand bond, coordination bond, acid base reaction, particularly Lewis acid, Lewis base, or Bonsett acid, they are all sigma covalent bond, am I right? So, non-covalent bond, hydrogen bonding, halogen bonding, chalcogen bonding, pi-pi interaction, ionic interaction, am I right? That all covalent bond. So, like a hydrogen bond, you remove the hydrogen, place a halogen there. So, that will be a halogen bond, non-covalent interaction. So, based on that concept, we have developed a catalyst. It is a very new concept coming up only last 15 years. So, that is the thing. But in today's talk, I will be talking more about metal nano catalyst. Okay. So, again, this is all 10th story again, I am taking slowly. So, there is a tortoise, it's very slow. The story I am not talking, the race between that I am not talking, that is only story, am I right? May not be reality. So, there is a tortoise, and generally what is the problem in our view, what is the problem with the tortoise? Why nobody is responding? Very slow, it is very slow, am I right? Yeah, its water is there? No, nothing is there. Water is reasonably fast, but generally it is slow. So, if it is slow, you feel it slow. That is what I said in our view. In your view, it is fast, in bracket water, that is also correct. So, in general or in the normal place, it is a slow. Okay. So, you want to imagine you are tortoise. Now, you imagine. So, you want to go somewhere, you will be very slow, am I right? Or put it like this. So, you want to go to gate, IIT gate, you want to go by walk, it will be very slow, am I right? It will be good for health, all secondary, but it is very slow. So, what you will think? Oh my God, when I go, one bus comes, it will be nice. Yes or no? So, I will go immediately. Our bus is also not coming, the time table shows it will take 15 minutes. Then if somebody comes in two-wheeler, you will ask for the lift, am I right? So, the what is the process? We want to make it fast, am I right? So, similarly, for example, if you have something like tortoise, you are like tortoise, then if you are used to normal system, am I right? If you are used to, that is a very important thing, then you want to have things faster, am I right? Like that, so many reactions are slow. That is the nature, like tortoise. So, tortoise will never realize it is slow, am I right? Because that is not used to the other things, but now you are used to everything, am I right? So, if the reaction is slow, for example, one reaction will take place for 10 days and you want to make a big scale reaction or you do in the lab itself, it takes 10 days. Can you wait for 10 days? Okay. If it is industry scale, then you have to rotate for 10 days. See, imagine so huge plant and power you need. So, it is not possible. Okay. So, you have to make it fast. So, that is a idea we will have how to make it fast. Similarly, if your reaction is very slow, then you have to make it fast. To make it fast, obviously you know that you need a catalyst. So, what catalyst does? How it will increase the speed? Huh? That is the thing. Okay. But this is a cartoonic representation I put. Okay. So, what you do now? You attach wheel. Then also it won't be fast unless otherwise you because that legs are tied, no, you have to push it. Okay, just imagine then you tie also one rocket, small rocket, not big one, okay, rocket. So, what will happen? It will be too fast, am I right? Sometime it may be fast or it may be too fast, it may lead you to accident also. Don't think that catalyst is always the way it will work the way you want, am I right? It can be either way, there should be a control, am I right? That is why this cartoon very nicely, see there is a helmet, alright. So, there is a helmet is shown, then so what the way you said, it reduces the activation energy, how much it reduces, that is also important. So, catalyst will increase the rate of the reaction, but in the way you want, am I right? So, that is the very important thing. So, we will come back to your 10th class definition. So, the cartoon is just to make you little bit involved, no? After seeing the tortoise you become quite active, right? So, otherwise it is boring always. So, catalyst, just remember your 10th class chemistry. Catalyst is basically a substance in a layman word, or in our language is a chemical, okay, that speeds the chemical reaction but not consumed and chemically unchanged at the end of the reaction. This is a definition for a catalyst. A catalyst is increasing rate of the reaction, but it will be involved in the reaction, but it should not be consumed. If that is the case, once the reaction is over, it should come out, again go for another catalytic cycle, again come out again and again. How many times it will go into catalytic cycle, that says the efficiency of the reaction, catalyst, am I right? So that's the thing. So the catalyst should be recovered. If it is coming out, then you should be able to recover and reuse it. That will make a more efficient catalyst or more economic catalyst. I will put it like that. And this whole process, the process is called catalysis. You might have heard this word catalyst, catalysis. Catalyst is a substance, am I right, which makes the process. Catalysis is a process. The whole process is called catalysis. Okay. So for a compound or chemical to be a catalyst, there are three important aspects what you have to know, that it should take part in the reaction. If it is not taking part in the reaction, so for example, you are setting up a reaction, you think that is a catalyst, you just put in the RB flask. Don't imagine that it will take part in the reaction and it will reduce the reaction rate, may not participate at all, am I right? So that it should participate, then it should alter the reaction. Altering can be either way, no? It can make it fast or it can make it slow also, am I right? Our aim is making it fast, but reality it can be either way. So it should possibly increase the reaction rate, then return to its original form. This is a catalyst. Then additionally you recover and reduce it. So that becomes more economic catalyst. Again, this is the basic what he has mentioned. So when you take a reactant A and B, you react and get a product AB. So in this process, there will be several transition states. Am I right? Depends on the reaction, and every transition state will have a different energy, and the one which is having highest energy will be the determining factor. Rate of the reaction will be determined, because ultimately if the reaction A and B reacts and gives product AB, so it will, this is simplified curve, am I right, graph, but reality there will be several activation energy, but one will be on the top. So it's a simplified one. So for example, you take this is the transition state. Why it's not working? Yeah, if this is a transition state, so from here to here the energy difference, we call it activation energy. If at all this reaction has to take place, the barrier has to be crossed. If the barrier is more, the activation energy is more. The barrier is less, the activation is less. Barrier is more, it will be slow. Barrier is less, it will be fast. For example, you take this is the activation energy curve, and you want to just you have to make the reaction. That means this stone has to go all the way, it has to come here. So depends on the height, you have to put the effort, whatever way it is. Okay, so it's more or less. If this is the uncatalyzed reaction, and if you are doing catalyzed reaction, then the activation energy has to come down. Am I right? The catalyst should be part of the reaction and part of the transition state. That's the point. And the activation energy should come down. For example, something like that. So if this is the uncatalyzed reaction and you are taking a catalyst, so it is involved in the reaction, then there are so many transition states, and the one which is having highest energy, that's activation energy, that should be less than uncatalyzed reaction. And what is the difference between the activation energy? That much the reaction will be faster. Am I right? So this is the thing. For example, you take a uncatalyzed reaction, so it takes some just time wise, and you have a catalyst that is reduced, it will be much faster. Am I right? So what do you understand when you talk about catalyst? We are talking about activation energy. More the activation energy, the reaction will be slower. Lower the activation energy, comparatively reaction will be faster. So, when you use a catalyst, it goes, takes part in the reaction, then new transition states are created. Okay. Among them, the highest energy transition state will be much lower in the uncatalyzed reaction. So, N the activation energy, the barrier is reduced, the reaction will be faster. So, this is the basics you might have learned already. So, we will not discuss. So, how important the catalysis area? Everybody will say that their area is the best, am I right? That's the way. That's the way. No? Whatever we think, that's the best. Even if we have whatever, that's a thing. But the data should explain you, am I right? The reality. So now, if you see this catalysis area, this is a data based on 2013, not updated one, little bit old data from this particular chemical and engineering news. So far 15 Nobel Prizes are given for the area of catalysis, which includes of course biocatalyst, enzymes, all those things. That is a big number, am I right? And 14% of the chemist, so far whoever got Nobel Prize, chemist alone 14%, and percentage wise, if you see the numbers, that is a 19%. So, that is really the overall I am talking about biocatalyst, metal catalyst, non-metal catalyst, all kind of catalysts putting together. This is the number based on at least a decade back. Okay. So, now you see this is the first person got the Nobel Prize in 1909, William Oswald. This word you might have heard, am I right? Who has coined the definition for catalyst, the principle of catalyst. So, fundamental principle of catalyst. So, that means the principle should have come at least 10-15 years before that, am I right? So, you got the Nobel Prize in the first 10 years. Then you see that after 3 years, this Paul Sabatier got the Nobel Prize, catalytic hydrogenation of organic compound. That reaction you might have heard, am I right? Palladium carbon hydrogenation or platinum carbon hydrogenation, vanaspati preparation, you might have heard, no? You take vanaspati, people say you do not eat it because it is saturated, because unsaturation you are reducing as a saturation. Okay. So, that is the thing. Now, you see in 2018 that Haber process, ammonia synthesis, you might have heard, is one of the revolutionary reaction in mankind, am I right? Otherwise, you will not have all these fertilizers and all those things. So, this initial stage, but later on you can see in 2001 Nobel Prize was given in the chiral catalyst. I discussed on in my previous lecture. Now, you can see 2005 coupling reactions, I do not know, this is olefin metathesis. Then 2010 palladium catalyzed coupling reactions, all this Heck coupling you might have heard, am I right? Suzuki coupling, I do not know whether you heard. So, all those guys got the Nobel Prize. And 2021 again another Nobel Prize for organocatalyst we discussed. 2022 this list is not updated. Click reaction, copper catalyzed click reaction, Sharpless got the second time. So, that is the list, I think you should have it here. Yeah, this is the thing. So, some of the thing I have listed. So, more than 15 times if I understand correctly, the area of catalysis got the Nobel Prize. Okay. This is very, very important. This is the award wise and value wise, economy, end of the day money decides everything, am I right? So, any chemical you make in the world, we make. So, 90% of the chemicals are made by catalytic process. If it is having more than one step, somewhere the catalyst process is involved. So, catalyst is unavoidable now, am I right? So, catalyst process is very important, and if you see the market value as on 2005, the catalyst process, I am not talking about catalyst price, catalyst process product price using catalysis process 63 lakh crore rupees, that is 900 billion. So, this value also keep on changes. This year I will say it's a 63 lakh crore. If it's the same slide, when I use next year, it will become 64 lakh crore. The Indian rupee goes down and dollar goes up, am I right? So, that is the way. I do not know which year I made this calculation, but close, more than 60 lakh crore rupees. There is a market value in 2005. 2000, this is all big number again. We cannot, so you have to compare where we stand. So, again I am coming back to 2005 Indian budget expenditure 5.42 lakh crore. Whereas, this is more than 10-fold whole Indian budget expenditure versus chemical product using catalysis more than tenfold. And what is the budget last year 2004? 48. Even the last year budget is much lower than 2005's chemical process value. So, that is the market value, the real market value what you have to understand. Okay. And only the catalyst, this we are talking about the chemical process, any chemical synthesized by catalyst. But what is the price of the catalyst? That has a market, no? So, you want to do now Grubbs metathesis, you have to buy the rhodium or the ruthenium catalyst. You want to do palladium Suzuki reaction, you have to buy a palladium catalyst. The catalyst itself has a market. So, that is also very high. You can see it here in 2010 and 29.5 billion, that is 2.06 lakh in 2010. You can see that is 2005, that is our almost our half of our Indian budget. The catalyst value itself is really huge. And not only that, in the world, most important process are catalytic process. Obviously, am I right? Otherwise, you won't be able to take it. First one, you can see it here, petroleum refining, cracking process. You know, we get always we talk about crude petroleum price, 1 barrel. Then people bring here, then they make petrol, no, natural gas, or you get petrol, diesel, kerosene or tar, whatever it is. A lot of things are coming from petrol. So, this process you break the bond, am I right? You take a huge molecule having 10 to 15, 20 carbon, you break it. So, then if you have 2 carbon, 1 carbon is a gas, am I right? 3, 4, 5 it's a petrol, more than that it's a kerosene, diesel or so on. Finally, you end up with junk to use make the road, am I right? So, this process is a cracking process, you might have heard, and that is one of the biggest process using catalyst. And you can see the 3.7 million metric tons catalysts are used, 3.7 million metric ton. I don't know how huge, am I right? You can't even imagine. So, that is the way it is, and the value of the catalyst is $5.6 billion. The second most important process, chemical synthesis, whatever chemicals we use in the lab, am I right? These are all in our industry. So, this is a chemical synthesis, that is again it is using a 4,58,000 metric tons worth $5.5 billion, again very huge. And third one, you can see it, polymer, most of our clothes, everything nowadays polymer. So, this is another big market using catalysis, 3,40,000 metric ton. The quantity of catalyst is used and value is 3.6 billion, and also the automobile industry, the emission related things all involved actually catalytic process. In future or presently, people are focusing more on, you also might have heard, right, all this fuel cell, then photovoltaics, all this solar panel, am I right? The efficiency is not, say for example, now I don't know, if you have a solar panel at your home, it is costed 2 lakh rupees, am I right? After 10 years, it may cost only 20,000 rupees, am I right? So, the efficiency, the research is going on. Now the efficiency of that panel, what you have is 6, it becomes 12. Then what you need is half of that, am I right? And so on and so forth. So, that is the way that. So, this is all going on. Biomass, making petrol, am I right? Not from the petroleum product, making from your agricultural product, am I right? Biomass you can make it, and natural gas conversion, so on and so forth. These are all now area people are extensively looking to develop new catalytic process to make it more efficient, whatever we have. If the petroleum product runs away, I mean it's all going to be over, then where you will get your thing? Either you have to go with electric car or you have to make it separately. So, there is a biomass and all comes in the picture. So, again, so far I discussed about catalyst. So, now slightly the next version, chiral catalyst, already I explained, am I right? So, I am not going to, just to brief you to make you to remember. So, chiral catalyst is used in asymmetric synthesis or enhanceable selective synthesis or stereoselective synthesis, whatever word. So, basically the aim is synthesizing up to active form, possibly single enantiomer. So, the catalyst will be chiral, am I right? That is the message what you have learned last time, and even this process I told last time, the most of the drugs what you buy in the pharmacy, more than 50% are single enantiomers, then this is all the value I have discussed last time. So, what you have to realize, the chiral catalyst, you have a normal catalyst. Now, if the catalyst is a chiral, we call it chiral catalyst, and chiral catalyst is used to make optically active compound. Okay. So, now we will go to nanocatalyst, then chiral nanocatalyst. Okay. So, now what is the concept to develop a new term? This 20 years back, I do not think we have this term nanocatalyst. Okay. It is a very new term, even for some of you it may be very new. So, for example, catalyst can be divided in several ways, in several categories, am I right? One important way of classification is homogeneous catalyst and heterogeneous catalyst. You should have already studied, am I right? So, homogeneous catalyst mean, most of, if you have walked into my lab, I think some students already came, 3 students, am I right? Yeah. So, you know, mostly we do homogeneous catalyst. Of course, we do heterogeneous catalyst also little bit. So, they might have, you might have seen, am I right? So, the reaction is going on, mostly clear solution. Okay. So, homogeneous catalyst means your catalyst and the reactant will be in one phase. That means clear solution. It's a if it is a solution phase, clear solution. Most of the academic labs we use homogeneous catalyst, because you might have seen what was the scale of the reaction. Whatever you have seen, at least in my lab, same for all the lab. What is the scale of a reaction? Did you ask? No, you should have asked. What is the scale of the reaction? How much catalyst you are using? That will be not more than 1 millimole. Am I right? Half millimole, 0.2 millimole. They might have told you, am I right? 0.5 millimole. Very so small, so small. That now reaction itself becoming nano reaction now. From mole, say 100 years back, everything is in mole scale. Then it became, when I was doing PhD, it became 1 millimole case. For us, standard reaction is 1 millimole. Now the standard reaction is 0.2 millimole. That's the way. Even the reaction, I mean, just in a lighter note, now this reaction can be called as a nano reaction. The scale is so small, from here to it became slowly small. Who asked the question? Oh, you are asking. Okay, you do 1 millimole scale reaction. Okay, you need 10 milligram of the catalyst. The catalyst cost is 1000 rupees. So, there you have to use 10 milligram, here you have to use 1 milligram, which will be cheaper? 1 milligram. So, now here you are using 1 millimole starting material. In a smaller scale, you will be using 0.1 millimole starting material. Just imagine the cost, everything will be reduced. Then you can ask me, then why 100 years back they didn't do in small scale? Am I right? We were not equipped. So, now you need only 1 milligram to record the NMR. Okay, you take 1 milligram, dissolve in 1 ml solvent. In that you take 1 microliter, inject in HPLC. But that time they didn't have anything. Am I right? Even the technology develops. So, now we are able to do at the small scale reaction. Am I right? So, that is a way it is. So, now most of the reactions in academic labs are homogeneous reaction, because if it is homogeneous reaction, only one phase. So, the reaction and reactant interact very well. So, the reactivity will be very high, selectivity will be very high. Am I right? Okay. If the reactivity is very high, that means the recoverability and reusability will be very poor. I told the catalyst has to be recovered and reused, am I right? Otherwise, it won't be economic. So, in research lab, you go and ask our students there, you ask them, are you recovering this catalyst? Today, if you have time, you go to any of the organic labs, there will be, some reactions will be going on, clear solution. You ask them, is it catalytic reaction? If they say yes, most probably they will say yes. If then you have to ask, are you recovering the catalyst? The answer will be no, because homogeneous catalyst you cannot separate easily, because they are in one phase. Am I right? It's very difficult, and if you want to separate, it's more expensive than the catalyst price. Am I right? Because that's a problem, and we are not worried because small scale reaction. Again, answer to the question. Am I right? We don't worry. Small scale, 1 milligram catalyst we use, recovering will be price of 10 milligram. So better you throw. We are happy. But you go to industry. Just now I showed all the petroleum refinery. You see all big boilers. all the catalysts will be in the kilogram. Okay, say for example, you are using palladium catalyst. 1 kilogram palladium will be like 4 or 5 lakh rupees. Am I right? Can you throw that 1 gram? There you cannot throw. So academic labs, they work with homogeneous catalyst, whereas industry, they cannot work with homogeneous catalyst because catalyst has to be recovered and reused. So they go for heterogeneous catalyst. What is the definition for heterogeneous catalyst? The catalyst and substance will not be in one phase. If you do a liquid phase reaction, you will see that there's a turbidity, am I right? You can see two, solid and mixture, you have to catalytic hydrogenation is heterogeneous reaction, am I right? So they will take two phase reaction. If it is not, since homogeneous, you can see the reactivity will be poor compared to the homogeneous reaction. Reactivity will be less, selectivity will be less, but recoverability and reusability will be more. So now you have to take a call when you are having we want to do a reaction, which one you want to use it, accordingly you have to decide. Mostly academic, they go with homogeneous catalyst because reactivity, selectivity we want, and we are not worried about recoverability, reusability. When it goes industry, they are also worried about, it's not that only recoverability, reusability, with good selectivity they will be happy, am I right? But it's not happening, but they say among these two this is better, they go with heterogeneous catalyst. Now the question is, so now if you take advantage of homogeneous catalyst, good reactivity, selectivity, but poor recoverability. The advantage of heterogeneous catalyst, good recoverability, reusability, but poor reactivity and selectivity. So if you have a catalyst which is having bridging only the advantages, that means good reactivity, good selectivity, good recoverability, good reusability. That will be very nice, am I right? So that is how the new concept nanoparticle as catalyst came in the picture. Aim, that's aim. How much successful? That is another question. So if we have a metal nanoparticle as a catalyst, theoretically, okay, ideally, it can have only the advantage of homogeneous catalyst and heterogeneous catalyst. How? You take the nanoparticle now, you know, you might have already heard a lot, am I right? So you have a bulk, say one solid, this much big rock, stone you have, imagine, and you break that stone into 10 pieces. Now you take 1 piece versus 10 piece, which will have more surface area. 10 piece, huge, am I right? So that's the concept. You take a nanoparticle and make it all small, they are small pieces, they're so tiny, that's a nanoparticle, am I right? Nano, can you imagine how small? You cannot even see it, am I right? Too small, so it behaves like a homogeneous catalyst, okay? But end of the day it's not soluble, so it behaves like a heterogeneous catalyst. So now you talk about reactivity and selectivity, it behaves like homogeneous catalyst because it's too small. So it behaves like homogeneous catalyst. But if you take recoverability part, end of the day anyway it's heterogeneous catalyst, okay? By using appropriate technology, you should be able to recover and reuse it. This is the concept. So now we will come to the chiral nanocatalyst. When you make a nanoparticle, we will discuss in the next few slides. So nanoparticles are not very stable, that you have to understand, because anything you see here in nature, they are stable, am I right? So in nature what you see is a bulk, not the nano, because nano is so active, reactive, it will collide and they will become macro particle, and finally bulk what you see in the normal way. So this process called agglomeration. So nanoparticles are not stable, they will further, they will collide, then it will become bigger particle, then so on and so forth. So to avoid this nanoparticle becoming macro particle, we have to use stabilizers. You have to stabilize the nanoparticle. Nanoparticles are not stable, you stabilize. So you stabilize the nanoparticle, the stabilizer is chiral, am I right? You take palladium 2, reduce it, palladium 0, nanoparticle, leave it, it will become palladium bulk black, silver mirror you have seen somewhere. that is basically some kind of nanoparticle, am I right? Like that, but it is useful for nothing because that silver 0, then later on it will become black and it is not activated. That's basically the nanoparticle becomes bulk. Similarly, if you have a nanoparticle, if at all you are making, immediately it will become a bulk. So you have to stabilize as a nanoparticle. For that, you have to use a stabilizer. And if the stabilizer is chiral molecule, then what will happen? The whole nanoparticle will be chiral. Am I right? That chiral catalyst, the catalyst will become chiral catalyst. So this is the idea for the metal chiral nanoparticle. Now you know what is catalyst from already, you know what is chiral catalyst, you know what is nanocatalyst, you know what is chiral nanocatalyst, that also you know. Am I right? The design what I am going to discuss about chiral metal nanocatalyst. So that much is good enough to understand. Then we will go to the research little bit. Okay. Okay, that's what. So the nanocatalyst. Now you bring the stabilizer chiral one, then it becomes chiral nanocatalyst. That's the idea. The overall the understanding of the area. Okay. So again, very basic slide before going, because this is a so very basic teaching I supposed to do. So again, we will go how small the nano, because if you don't understand, you might have seen all those things, but still. So nano catalyst, how small? Nano is too small, that much you know, am I right? But how small? So when we call a compound as a nanoparticle, you make a compound. You are telling something. Okay, that is 10 to power of minus 9 is a nanometer. Okay, that is correct. The question is, what is nanoparticle? What is nanometer? Further, any particle with a nanometer size is called nanoparticle. Am I right? 10 to the power 9 is nanometer. So any compound in nanometer is called nanoparticle. Okay. So when we call a compound as a nanoparticle, if the size of the particle is generally from 1 to 100 nanometer, more than 100 nanometer, then it becomes bigger. Okay. So how big? Again, this whatever say, how again try to understand. 1 meter, we know that is 100 centimeter. Am I right? And 1 centimeter is 10 millimeter. Regular scale we use it. Am I right? So that is so 1 millimeter, that is 10 power minus 3. Then 1 micrometer, 10 power minus 6. Correct? Then you go to nanometer, 10 power minus 9. Then angstrom, 10 power minus 10. So generally we will see the small, all those things, nano, nm, nanometer, UV, all you will see nanometer. Am I right? Or angstrom also you will see 10 power. That's the next small scale. Okay. So now you take it 1 micrometer, 10 power minus 6, that is 1 millionth of a meter. When you say 1 micrometer, in a meter, 1 by million, that is 10 lakhs, that much small. You talk about nanometer, 1 billion, then billion mean immediately you have to think what is billion, am I right? So 1 billion mean how much? 100 crore. We have a 1.4 billion population. Use that as a reference, am I right? 148, 105. So 100 crore. So 1000 million maybe 1 billion. I understand. That's what I understand. It's okay. So not that means when you say 1 million, 1 billion of, I mean we cannot say that's a way. We cannot go more than that. So okay. So now you come here. So you take our hair. Okay. So you see that I'm not talking about the length, the width. Also it will vary, but in general that will have 50 micrometer. Our hair thickness is 50 micrometer, and so 1 millimeter mean 1 by 5000 thickness of a hair. So our hair is 50 micrometer. So in that 1 by 5000, that means small, that's a nanometer. That is the particle size we are talking. You have to understand that is basically having only few atoms. You say this is a compound nano wire. So the width will be few nanometers. That means there will be only few atoms will be there. Then atom is much smaller. Am I right? So, size of atom molecule all you can consider. So, that much small nanoparticle particles we are talking. So, why nanochemistry? Actually 10 years back this was very hyped topic, everybody was talking nano, but now little bit has come down, because every field there will be hype, then whether it will be true realistic or not, that time will give the answer. Okay. But why people talk about nano? So, something. Yeah, you were saying. I want to. Its area will be increasing. That's what you are saying. Yeah, in a way is correct. So generally, when you have the particle in nanoparticle size, is physical property, chemical property, even biological property will be different. So when particularly in that size, that's why people were trying to do everything in a nano scale. Not always, sometimes is good, sometimes may not be as good as it is. Then if it is good, you take it, otherwise you leave it. Am I right? So this is the way this area became very popular. When you make the compound in nanoparticle size, it is completely different from the bulk material. Not always, but some of the times. How much it is different? Now take a gold. You know gold, all of you know, some of you, not all of you, some of you at least already wearing now. That's a bulk gold, am I right? Nice, solid, nice yellow color or gold color. Gold itself is colored now, am I right? So now this is the gold. But you make a nanoparticle of gold and disperse in a solution. Now you can see it here. So this is 100 nanometer, slowly the size increases. This is 1000 nanometer. Same gold metal, not gold salt, same gold metal. You make small particles. Now you change the particle size. See the color, it's not gold color anymore. Even the color changes. Am I right? And you increase the particle size, the color also changes from some kind of red to all the way it goes to purple or blue something. Am I right? So this is one example. The same gold, it's not gold 1, gold 2, it's not a gold acetate or gold carbonate, nothing. Same metal gold, 0 metal gold. You make a size, different size, disperse in the particular solution, the color changes, you can see it here. That's one example to tell you that same compound, when size changes, property also can change, not will change, can change. If changes, then it's good for you, take it, otherwise you leave it. All right. So how to make the nanoparticle? Because we have to make nanoparticle to use as a catalyst, am I right? That's what we are thinking. So there are generally two methods to make general. Okay, two method. Nanoparticle means small particle. Okay, you take a bulk, okay, and cut it by some means. Don't ask me, sir, how you will cut with knife size and all. Don't ask me. That's a method. Okay, so this is called top down method. Also, you might have heard, am I right? Other one, bottom up method. Bottom up method, you make an atomic small size, then goes for agglomeration, then nanoparticle will form. If you don't stop it, it will go for bulk. Okay. So one is bottom up, top down method, and most commonly what we use it is some kind of bottom up approach. So take generally in the lab, if you walk into our lab, you can ask if at all they are doing it. You take generally metal salt, okay, palladium 2 or copper 2, nickel 2, you reduce it, am I right? That can be done. Silver mirror test, am I right? So you are reducing where the aldehyde will be oxidizing to acid, am I right? So that means metal is getting reduced, silver mirror, that's a, see what you see is a nanoparticle. Then capping reagent, that's nothing but stabilizing reagent, because nanoparticles are not stable. Once you even make nanoparticle, it will become a bulk. So now active nanoparticle is formed. Now you use the capping reagent or stabilizing reagent and stabilize at nano size. Then it becomes nanoparticle and stable to some extent. Okay, this is the very common method to make a nanoparticle in the laboratory, at least the one what we are using. So when you use nanoparticle, the so called nanoparticle as catalyst in a nanoparticle size, we call it nanocatalyst. Basically, it's a catalyst sized in nanometer. So the easy term is nanocatalyst. And what is the advantage when you use nanoparticle as a catalyst? Yeah, the surface is enhanced, that's the most important thing. If the surface is enhanced, then the overlap, the contact between catalyst and the reagent will increase, am I right? So, then once the interaction increases, then it will behave like a homogeneous catalyst, am I right? More surface area, that's a point, and end of the day it will behave like a homogeneous catalyst, but it's not soluble in the medium, and but it's so small it will look like homogeneous catalyst, okay, but in appropriate process it's exactly heterogeneous catalyst, so easily you can recover and use it. So it will behave like a homogeneous catalyst, it will behave like a heterogeneous catalyst, and another advantage, you can tune the catalyst, am I right? When you make a nanoparticle, so how you reduce it, whether you want to have 5 nanometer, 10 nanometer, 15 nanometer, you can optimize the reaction, and how to stabilize, again different stabilizing agent, you can tune the way you want, okay. And on end of the day, the another point which I forgot to tell you between homogeneous and heterogeneous catalyst, nowadays you might have heard this word metal impurities in the final pharmaceutical product, you might have heard, am I right? For example, in the last step you are using palladium, homogeneous catalyst, the product will be always contaminated with the palladium, there will be some metal will be contaminating the product, and very difficult to, it's called metal trace impurity, very difficult, and it happens in homogeneous catalyst. But in heterogeneous catalyst, since it's binding with so many things, it cannot go and spoil the catalyst. But there's another word called leaching, you might have heard. So if from the heterogeneous catalyst only the metal comes out and in the solution, then it becomes homogeneous catalyst. So this is a serious problem of a metal nanocatalyst. So whether leaching is happening or not, you have to make sure there is no leaching. If at all leaching happens, then metal contamination will take place, okay. Generally heterogeneous catalyst, if it is a good catalyst, stable catalyst, then leaching should not happen. If leaching is not happening, then you can use in the last step of the medicine synthesis, then metal contamination will not be there, because most of the metals are toxic, am I right, and it is not allowed more than a particular amount, then that will lead into a problem. So again the difference between homogeneous and heterogeneous catalyst, metal leaching or metal contamination will not be there, and that is the advantage of nanocatalyst as well. Nanocatalyst supposed to be stable, but reality the heterogeneous catalysts are generally not very stable, leaching can happen. Then you have to prove that there is no leaching, or if leaching is happening, how much leaching is happening, okay. So now we will come to, okay, now 1 hour, so I will stop it here.
SwayamPrabha, Digital India, Educated India.